In this module, the whole focus is drawing Lewis structures. So we've talked about Lewis structures. That's that 2D representation of how the molecules are actually connected. We need to be able to do this so we can put it into a 3D world where we're using VSEPR. That's going to be the next set of modules we do. VSEPR, valence shell electron pair repulsion theory, how the molecules are actually connected in 3D space. So let's go ahead and work through these examples. Note on these that not only are we drawing the Lewis structures, we're labeling formal charge on all atoms and, if necessary, using resonance. The first set of molecules we're going to look at, we're just given the name. You should be able to go from name to formula to actual structure. So acetic acid. Even if you don't remember what acetic acid is, we know our naming rules. We know that ic acid comes from an ending of 8. So acid, acetic, we're going to cross off that ic part. So ACET, ATE, that is acetate, and that is an A. We should know acetate. Some of you guys write this as C2H3O2 minus, which is totally fine. The reason I always write this as CH3COOH or COO minus is because of this right here, because of the way it's connected. Now, when you have an acid, you have taken that anion and given it enough protons to make it neutral. In this case, this only has one negative charge, so I'm going to give it 1 proton. Most of the time, we're going to write that proton at the front of the molecule, but acetic acid is what we call an oxyacid, where the hydrogen is bonded, or the H+, to an oxygen atom. How do I know that? Because if I have an acid and it has oxygens in it, it's going to be bonded to the oxygen. The hydrogens are going to be bonded to the oxygen. So I've got this structure, and I'm telling you this is how it's connected. Let's go ahead and add up our valence electrons. We have 2 carbon. Each carbon has 4 valence electrons. Overall, 4 hydrogen. Each hydrogen has 1 valence electron. And 2 oxygen. Each oxygen has 6 valence electrons. 2 times 4 is 8, plus 4 is 12, plus another 12. I have 24 valence electrons overall. I'm going to go ahead and draw out my molecule. Now again, I intentionally write it this way because it's the way it's connected. Some of these, we write them the way they're connected, and you just have to kind of trust the process, and the more you practice, the easier it is to see that they're connected this way. When I write CH3, hydrogen can only have 1 bond. So, by writing CH3, I know that those hydrogens have to be bonded to the carbon. The hydrogens are listed right after the carbon. Excuse me. The hydrogens are listed right after the carbon. Therefore, they have to be bonded to the carbon they're listed after. Next up, I have another carbon listed. That's going to be bonded to my first carbon. Carbon is unique in the fact that it likes to bond to itself. A lot of atoms don't actually like to bond to themselves. They like to bond to other things outside of forming diatomics or the polyatomic of like P4, AS4, S8, and SE8. I then have an oxygen. That's kind of a long line. I have an oxygen, and I have 1 more oxygen and a hydrogen listed. Now, this is not completely intuitive, and I know that, but carbon is going to have another oxygen bonded to it, and that hydrogen is going to be bonded to the oxygen here. How do I know that? Well, I know it's an oxyacid, so I know that the hydrogen has to be bonded to an oxygen. But I also know that oxygen doesn't really like to bond to itself, so it's not going to form this. This is not going to happen. Don't do that. This, not very stable, actually quite reactive. And so again, the more practice you do, the more you're going to see this happen. Acetic acid is what we call carboxylic acid. And they have a very set structure. I'm going to go ahead and give all of my outer atoms their octet. I've got hydrogens, I've got the oxygen, giving it its octet. Now I check my inner atoms and give them their octet. I give this oxygen its octet. I'm going to check really quick how many electrons I've used up. I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up all of my valence electrons at this point, except when I check this carbon right here, it does not yet have its octet. So I'm going to have to form a multiple bond somehow. What I find is that the multiple bond is going to come from this oxygen atom donating a pair of electrons. Why is it going to be that oxygen atom? Well, if I check the formal charge, I would see that oxygen is -1, the carbon is +1, the oxygen over here is 0. Remember, oxygen with 2 bonds, 2 lone pairs is 0. So that's how I'm going to be able to tell, is by checking my formal charge. But let's go ahead and donate that. So it doesn't matter which pair of electrons you pull. I usually just pull the top one, sticking them out of the way. And it's going to form a double bond of the carbon. Now I'm going to check formal charge overall. Whenever hydrogen has 1 bond, it can't have more than 1. Don't give hydrogen more than 1. It literally can't do it. It's going to have 0 charge. We talked about how when carbon has 4 bonds, it will have a 0 charge. It does not matter if it's 4 single bonds, 2 single and a double, 2 double, or triple and a single. It will have 0 formal charge. When oxygen has 2 bonds and 2 lone pairs, it also has a 0 formal charge. That does not matter if it's 2 single bonds and 2 lone pairs, or 1 double bond and 2 lone pairs. It will have a 0 formal charge. And this is your structure of acetic acid. If you need to write this down, please pause the video to do so, because I'm going to erase everything in here. Now next up is nitrogen dioxide. Notice the way this is written. Nitrogen and oxygen are both nonmetals, so this is going to be a covalent compound or molecular compound covalently bonded, so we're using the di to emphasize how many I have of something. There's no prefix in front of my nitrogen, so I just have 1. Di means 2. Oxide means oxygen, so NO2. Now this example, I told you guys you wouldn't have to draw yourselves, and it's true. I'm showing you what it would look like if you have an odd number of electrons. When I add this up, I'm going to end up with an odd pair of electrons. I'm going to show you what it's going to look like, but I'm not going to do that to you on an assessment, okay? I want to show you how we handle it, but also recognize that if you add this up and you somehow get an odd number, that means you've added up your valence electrons incorrectly. Because I won't give you this example on an assessment. Nitrogen. 1 nitrogen has 5 valence electrons. 2 oxygen. 2 oxygen. Each one has 6 valence electrons. Overall, this gives me 17 valence electrons. Now, nitrogen is listed first, and it's less electronegative, so it goes to the center, and it's connected to our 2 oxygens. We're going to give our oxygens their octet, because they are our outer atoms. Now check how many of your valence electrons you've actually used up. We've used up 2, 4, 6, 8, 10, 12, 14, 16. We've used up 16, and we have 17 to distribute. Any excess electrons go to your central atom. Now you're going to check to make sure your central atom has its octet. My central atom does not have an octet. In fact, it only has 5 electrons. So we're going to go ahead and do the donation. One of the oxygens is going to donate a pair of electrons to that nitrogen. We have now formed a double bond here. I'm going to check again. Nitrogen still doesn't have an octet. The issue is nitrogen now has the equivalency of 7 electrons. 4 here, 2 here, and 1 here. Nitrogen cannot go past an octet. So if I was to donate another pair to make a double bond, I would end up with overall 4, 4, 1. I would end up with 9 electrons. And I can't do that. Nitrogen cannot go past an octet. It doesn't have the space. So this is going to be the structure. Now, I'll talk about resonance in just a sec, but let's go ahead and assign the formal charge. Oxygen, when it has 2 bonds and 2 lone pairs, is a 0 charge. Doesn't matter that it's a double bond, that's still 2 bonds. Oxygen over here, this oxygen, does not have that. It does not have a 0 formal charge, so let's check what it is. Formal charge is the number of valence electrons minus the number of lone pair electrons, 1 for each electron, minus the number of bonds. 6 minus 6 minus 1 gives me an overall -1 charge. Again, the 2 down here was just to label it differently from the first oxygen. Let's check my nitrogen. Nitrogen has 5 valence electrons. This nitrogen has 1 lone pair electron and 3 bonds. 5 minus 1 minus 3 plus 1. Now the overall formal charge has to equal the overall charge in the molecule. The molecule has a 0 charge. And when I look at this one, it's kind of messy. Let me rewrite that. I have plus 1 minus 1 giving me an overall 0. So it is a valid Lewis structure. It is also, though, a radical because it has an unpaired electron here. So it can't follow the octet rule. It just can't. It doesn't have the right number of electrons. But backing up just a little bit, why did I give the double bond to that oxygen nitrogen? Why didn't I do it with the other oxygen instead? Drawing our lone pairs in. This would now have a -1 formal charge. Plus 1 still on the nitrogen and 0 on this oxygen. Both of these structures are valid. This is called resonance. Neither one is contributing more than the other. They're both equivalent. They're both valid. They're both equivalent. They both contribute to the resonance hybrid, but they are resonance structures. Okay, go ahead and pause if you need to draw all this out. Let's talk about oxalic acid. Oxalic acid, ic acid. Ic comes from 8. So oxalate. I know oxalate is C2O42 minus. So I must have 2 protons to make this neutral, H2C2O4. I have hydrogens, I have oxygens, and I told you it's an acid. That is an oxyacid. So the hydrogens are connected to the oxygen. I've got carbon, oxygen, carbon, oxygen, oxygen, oxygen. How do I know all the oxygens are connected to the carbon? Carbon, there's 2 of them here, but they're going to be the central atoms because they're the least electronegative. Oxygen doesn't want to bond to itself. Carbon's fine bonding to itself. Carbon's also the least electronegative, so it's going to be in the center. There's 2 of them, so they both happen to be in the center, connected to the oxygens. And I know the hydrogens are connected to my oxygens as well, because again, this is an oxyacid. Move this over just a little bit. Let's go ahead and give our outer atoms their octet. And our oxygens their octet. And I always forget this part. Let's add up our valence electrons and see how many we actually have to distribute. We have 2 carbon, 2 times 4 valence electrons, 2 hydrogen, 2 times 1 valence electron, and 4 oxygen, 4 times 6 valence electrons. So we have 24 from the oxygen plus 2 from hydrogen is 26, plus 2 from carbon, another 8. We have overall 34 valence electrons. How many have we used up so far? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. We've used up all of them. That's perfect. Next thing we want to do is make sure all of our central atoms have their octet. I made sure to give the oxygens its octet, but I didn't check anything else yet. And I noticed that my carbons here need an octet. They're going to do this by forming a double bond. The oxygen here is going to donate a pair of electrons. The oxygen here is going to donate a pair of electrons. Why does the other oxygen not donate? Because oxygen doesn't want more than 2 bonds. It's already got 2 bonds. This already has 2 bonds. This already has 2 bonds. They don't want to donate more if they don't have to. So let's go ahead and draw in your double bonds. Now my carbons have their octet. Now let's check your formal charge. I know when hydrogen has one bond, it's got a 0 formal charge. I know if oxygen has 2 bonds and 2 lone pairs, it has 0 formal charge, whether that be 2 single bonds and 2 lone pairs or 1 double bond and 2 lone pairs. I know once carbon has 4 bonds, it has a 0 formal charge, whether that be 4 single, a double and 2 single, 2 double, or a triple and a single. So all of the atoms here have a 0 formal charge, and this is your Lewis structure for oxalic acid. Go ahead and pause it, because I'm definitely going to erase the rest of this now. Okay, what about perchlorate? What is perchlorate? Well, it's one of our polyatomics, right? Cl O4 minus. So I've got Cl, 1 chlorine, so 1 times 7 valence electrons, 4 oxygen, 4 times 6, sorry, I'm doing the math already, 4 times 6 valence electrons. That would give me 24 plus 7, or 31 valence electrons. But notice here there's a negative charge. When you have a negative charge, you need to add an extra electron, because these are counting the electrons, and I have an extra electron. 32 valence electrons. The chlorine is going to be my central atom. It's less electronegative than oxygen. It's tied for 3rd place with nitrogen, but oxygen is in 2nd place. It's also listed first. And go ahead and connect my oxygens. Give your outer atoms their octet. Check to make sure your essential atom has its octet, and it does. It has its octet. So now we want to look at formal charge and see, is this compound actually complete? Well, each oxygen has 6 valence electrons. It has 6 lone pair electrons and 1 bond. 6 minus 1 is a negative 1 charge. Each oxygen here has a negative 1 charge. What about the chlorine? Chlorine here, 7 valence electrons, no lone pair electrons, and 4 bonds. Overall, a +3 formal charge. Now, you could say, okay, well, I drew a Lewis structure. You did, but it's not valid. You need to minimize your formal charge. We can do that by forming multiple bonds. What if this oxygen donated to here? Well, how would that change my structure? Well, it would get rid of a lone pair here. Got a double bond here now. This oxygen now has a 0 formal charge. The chlorine now has 1, 2, 3, 4, 5 bonds. And an overall +2 charge. But if that oxygen can do it, why can't another? What about this oxygen? If this oxygen donated a lone pair, one, two, three, four, five, 6. Chlorine now has 6 bonds, +1 charge. This oxygen is a 0. The chlorine is now a +1 charge. Could I further minimize though? Yes, I could. What if this oxygen also donated? Now this oxygen has a 0 formal charge. I look at the chlorine. Chlorine has 7 bonds now. 7 minus 0 minus 1, overall 0 formal charge. 2, 3, 4, 5, 6, 7. Now, I did pick 3 random oxygen atoms to do the double bonds to. What if I had done different ones? What if I had used the other oxygens instead? Those would be what we call equivalent resonance structures. Try to move this out of the way. What I mean by that is this is one possible resonance structure. And normally we'd write the -1 charge up here. This is completely equivalent to writing those oxygens in a different, or the double bonds in a different oxygen though. So I could have also written ClO, 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 ClO with our lone pairs. These are equivalent structures. And distinguish the two, we put those resonance arrows that look like this. I could have written ClO, let's see, O in a single here. Or I could have put the single bond up top. These are all completely equivalent resonance structures. All have minimized formal charge to the best of our ability. All have they all contribute to the overall true resonance hybrid. Go ahead and pause if you need to write all of that down. Okay, what about azide? Students mix up azide and nitride. Azide is N3 minus, or azide is N3 minus. Notice that sounds the same. Azide means I have 3 nitrogens bonded together. Nitride is a single nitrogen that has lost 3 electrons. So 3 nitrogens, 5 valence electrons each. (15 valence electrons), but it does have that -1 charge, so I'm going to add 1 more valence electron. 16 valence electrons. There's 3 nitrogens, so they have to be connected. And I'm going to give the outer atoms their octet. Now I check and I see, does my inner atom have its octet? It does not. So I'm going to make multiple bonds to give it its octet. Now, I could do that a few different ways. I could say, okay, well, how about we have this nitrogen here, don't need a pair of electrons, and this nitrogen here, don't need a pair of electrons. That would give me N, double bond N, double bond N, and each nitrogen on the side would end up with 2 lone pairs. I'll do the formal charge in a minute. Because I could have also said, how about this first nitrogen, donate, I erased one by accident. I thought I'd erased one. Okay. Donate 2 sets of electrons. Well, that would give me N, triple bonded to N, single bonded to an N, whereas this nitrogen still kept its 3 lone pair of electrons, but this one only has 1 lone pair now. But you probably see the trend now. What if it was that last nitrogen that donated 2 pairs instead? Now it only has 1 lone pair. And this nitrogen on the left-hand side has 3 lone pairs. I'm going to check my formal charge. None of these nitrogens, oh wait, I lied. So nitrogen, when it has 3 bonds and 2 lone pair electrons, is a 0 formal charge. So this nitrogen's a 0 formal charge, this nitrogen's 0 formal charge. So triple bond, which is 3 bonds, and then 1 lone pair. The other nitrogens are all going to have a formal charge of some sort, though. Look at this central nitrogen here. Nitrogen has 5 valence electrons, no lone pairs, and 4 bonds. It's overall +1 charge. All of them in the center have a similar fashion. They all have 4 bonds and no lone pairs. So they're all a +1 formal charge. What if nitrogen has 2 lone pairs and 2 bonds though? Nitrogen, 5 valence electrons, 4 lone pair electrons, and 2 bonds. -1, and this one will also be a -1. Notice overall here, -1 + 1 -1 gives me an overall -1 charge, so I'm still matching to the overall charge of the atom, N3-. But what about the last nitrogen shown in these two structures where it has 3 lone pairs and 1 bond? Nitrogen, 5 valence electrons, 6 lone pair electrons, and 1 bond. 5 - 6 - 1 gives me an overall -2. So I've got all my structures in. Now, these structures are not equivalent. How do I know they're not equivalent? I wrote that -2 on the wrong side. I apologize. That -2 should be written on the one that actually has a -2 charge. This is the -2. That is 0. How do I know what's equivalent here? I mean, here I've got charges everywhere. Whereas here only 2 atoms have charges. But the charges are larger. So how do I know what to do? Well, the biggest thing is we want to minimize formal charge. And by minimizing, I mean the smallest numbers possible. This one has minimized formal charge. None of the structures are perfect. But this one will contribute most because my charges are just +1 - 1. These two will equally contribute least due to that larger difference in charge. All 3 contribute to the true resonance hybrid. So all 3 mix to give me the true resonance hybrid. These again are your resonance structures. What about chlorite? So we know perchlorate is ClO4-, which means chlorate is ClO3-, which means chlorite is ClO2-, and hypochlorite is ClO-. So ClO2- is going to be hypochlorite. ClO2- chlorite. Sorry, I was reading this and seeing we're going to need hypochlorous in a little bit. So we're going to need that Cl- in just a little bit. Chlorite. 1 chlorine. 7 valence electrons. 2 oxygen. 2 × 6 valence electrons. 2 × 6 is 12, plus 7 is 19. -1 charge. We add 1 more valence electron. 20 valence electrons. Chlorine is going to go in the center, connected to my 2 oxygens. Give your outer atoms their octet, and see how many electrons you've used up so far. 2, 4, 6, 8, 10, 12, 14, 16. I've used up 16, I have 20. Add your extra electrons to the central atom. 2, 4. I've now used up all 20 electrons. Check to make sure your central atom has its octet. It does have an octet. Now you're going to check formal charge. The oxygens here are not minimized in their formal charge. They don't have 2 bonds and 2 lone pairs. They're going to have a formal charge, but they are equivalent. Oxygen, 6 valence electrons, minus 6 lone pair electrons, minus 1 bond each, negative 1 charge each. Chlorine, 7 valence electrons, 4 lone pair electrons, 2 bonds, plus 1 charge. Can I minimize this charge further? On the nitrogen, I didn't have much choice. I couldn't go past an octet on that central nitrogen. Nitrogen cannot have more than an octet, but chlorine can. This oxygen can donate a pair of electrons to minimize this formal charge. If it does that, this oxygen will now have a 0 formal charge. Let's check our chlorine. Seven valence electrons minus our 4 lone pair electrons minus our 3 bonds gives us an overall formal charge of 0. Again, there's no reason that the double bond had to go to that oxygen, though. This will form a resonance structure with a completely equivalent structure where the double bond is on the other oxygen. Again, I say these structures are equivalent because neither one contributes more than the other because of the formal charge. Let's see, 4 electrons there, 6 here, 2 and 2. So the formal charge here, now 0, 0, minus 1. And again, the minus 1 because it matches the overall charge on the ion itself. Both of these contribute equally. What about bicarbonate? What does that mean? Well, I know carbonate is CO3 2 minus. I know the word bi means 1 hydrogen has been added to it. 1 H plus specifically. So I've got an H plus, a CO3 2 minus, giving me HCO3 minus. It might be hard to recognize this, but this is an acid and a base. It's an amphoteric species. It can act as either. And it's an oxyacid, so that hydrogen is attached to the oxygen. We have 1 hydrogen, 1 valence electron, 1 carbon, 4 valence electrons, 3 oxygen, 3 times 6 valence electrons. So 3 times 6 is 18, plus 4 is 22, plus 1, 23 valence electrons. We have a negative 1 charge, so 1 extra valence electron. Overall, 24 valence electrons. Carbon is the least electronegative, so it's going to have the oxygens connected to it. And the hydrogen is going to connect to 1 oxygen. Which one? I don't care. Doesn't matter. Let's give our outer atoms their octet. Hydrogen can't have an octet. Check how many electrons we've used up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used up all of our electrons. Now we're going to check and see if our central atom has its octet. And it does not. Carbon needs 4 bonds. Or some kind of lone pair to give it an octet. Carbon is not happy. So how can we make it happy? One of these oxygens will donate a lone pair to form a double bond to carbon. Sorry, I keep trying to change the size and hitting the wrong button. Let's check the formal charge. I know oxygen with 2 lone pairs and 2 bonds is 0 formal charge. Hydrogen with 1 bond is 0 formal charge. Carbon with 4 bonds is 0 formal charge. The oxygen here, 6 valence electrons, 6 lone pair electrons, 1 bond, negative 1 charge, which matches to the ion itself. Now, again, there's no reason why I had to give the double bond to that specific oxygen It could have gone to either one. So this is going to form a resonance structure. With this, which is chemically equivalent, meaning that neither one contributes more than the other. The resonance structures are equivalent. So this would have a -1 formal charge, 0, 0, 0, and 0. And again, the resonance structures are equivalent. Neither one contributes more than the other. On to cyanide. Cn minus. 4 valence electrons for carbon. 5 valence electrons for nitrogen. And I'm adding 1 valence electron for that negative charge. So 5 plus 4 plus 1, 10 valence electrons. I'm going to give one of them their octet. Let's just start with nitrogen. 2, 4, 6, 8, and then give carbon its 10. Carbon does not have an octet yet, so nitrogen definitely needs to share some electrons. If nitrogen shares 1 set of electrons, carbon still does not have its octet. So nitrogen needs to share a second set of electrons. Now if I look here, carbon and nitrogen each have their octet. Carbon has 3 bonds. So let's look at the formal charge. 4 valence electrons, minus 2 lone pair electrons, minus 3 bonds, and overall -1 charge. Nitrogen, when it has 3 bonds and 1 lone pair, has a 0 formal charge. It doesn't matter if it's a triple bond, double in 1 single, or 3 single, but it will have a 0 formal charge. Now, technically speaking, nitrogen would love to carry that negative charge over carbon. Nitrogen is more electronegative than carbon, but it doesn't have a choice in this matter. It's kind of like how we do carbon monoxide. Same situation, the carbon's going to have to carry that negative charge. Let's look at hypobromite. So, bromite is like the chlorate-chlorite series. We said earlier that perchlorate was ClO4 minus. So we know that chlorite is ClO3 minus. So that made, chlorate, I apologize. Chlorite was ClO2 minus, and hypochlorite was ClO minus. Hypobromite follows a similar pattern. Hypobromite would be BrO minus. This would be perbromate, bromate, bromite, and then hypobromite is BrO minus. We've got 1 bromine, 7 valence electrons, 1 oxygen, 6 valence electrons, plus 1 extra negative charge for that negative charge on the ion. 7 plus 6 plus 1, overall 14 valence electrons. Bromine connected to oxygen. I've used up all my electrons. Now let's check our formal charge. We've used up 14 electrons, 2, 4, 6, 8, 10, 12, 14, and everyone has their octet. So technically this is valid, but let's check our formal charge. Bromine, 7 valence electrons, 6 lone pair electrons, and 1 bond, overall 0 charge. Oxygen, 6 valence electrons, 6 lone pairs, 1 bond, -1 charge. The compound's correct. The formal charge is adding up to the overall charge of the ion, which is a -1, and oxygen is more electronegative than bromine. It's going to want to carry the negative charge. So this is the correct Lewis structure for hypobromite. Br with 1 single bond to oxygen carrying that negative charge. What about nitrate? My favorite polyatomics. NO3 minus. Nitrogen, 5 valence electrons. 3 oxygen, 3 times 6 valence electrons. Plus 1 valence electron for that negative charge. 3 times 6 is 18, plus 5 is 23, plus 1 is 24 valence electrons. Nitrogen's going to go to the center, connect to your oxygens. Give all of your outer atoms their octet. Check to see if your central atom has its octet. It does not have an octet. So one of these oxygens need to share and donate a pair of electrons. Now nitrogen has its octet. Let's go ahead and check our formal charge. We know if oxygen has 2 lone pairs and 2 bonds, it has a 0 formal charge. The nitrogen here has 5 bonds, 5 valence electrons, no lone pairs, and 4 bonds, so an overall +1 charge. The oxygens are the same. They each have 6 valence electrons, 6 lone pair electrons, and 1 bond, giving each oxygen a -1 charge. Now, we have been taught to minimize formal charge, and normally we would want to. We theoretically could make another bond between the nitrogen and oxygen, one of these oxygens, one of these two here, and say, okay, we're minimizing formal charge. But we can't do that because nitrogen cannot violate the octet rule. It doesn't have the space to put the extra electrons. It cannot violate it. It cannot have more than 8 electrons. So this is the best we can do. Now this does have resonance structures because you could put that double bond of oxygen in any of those positions. So I could also write this as N to O, double bond O, O, put my lone pairs in. Oops, sorry. Most often we put a -1 up here just to show the overall compound is negative charge. Or I could write the double bond to the bottom oxygen on the right-hand side. This is still +1, -1, 0, -1, -1, 0, -1, +1. They are equivalent resonance structures. Neither one contributes more than the other. They're all equivalent, and they're contributing equally to the resonance hybrid. What about hypochlorous acid? Acid came from. Don't get that hypo confused with hydro. Acid comes from, comes from ite. Don't get hypo here confused with hydro. Hydroic comes from ide. But comes from ite. So hypochlorous acid is HClO. But you're going to see this also written as HOCl. And that's because we've got an acid that has an hydrogen and oxygen again, which means it is an oxy acid. The hydrogen will be connected to that oxygen. ClO and H. So oxygen almost behaves as a central atom here. Let's go ahead and add, let's add up what electrons you actually have here to use. Chlorine, 7 valence electrons. Oxygen, 6 valence electrons. Hydrogen, 1 valence electron. Overall, 14 valence electrons. add in your get your octet on your outer atoms. 2, 4, 6. Finish off your inner atoms. Let's make sure we used all your electrons up. 2, 4, 6, 8, 10, 12, 14. We've used all of our electrons, and that's the correct Lewis structure. Let's go ahead and confirm with formal charge. If I look at the chlorine, chlorine has, sorry, I keep flipping between too thick of a font. Chlorine has 7 valence electrons, 6 lone pair, and 1 bond. 0 formal charge. Oxygen, when it has 2 lone pairs and 2 bonds, is 0 formal charge. And hydrogen, when it has 1 lone pair, is 0 formal charge. So we have our completed Lewis structure for hypochlorous acid. I apologize for the next one. I actually had the wrong structure listed. I don't know what I was thinking when I wrote it out, but I mixed it up. I actually wanted to do phosphorus tribromide. Bromine pentaphosphorus is not a thing. It's not even spelled correctly, so I don't know what I did when I typed it up. I caught it before I made my notes, but not before I made the PowerPoint and started making this video. So please change this one to phosphorus tribromide. It should not be what's listed in your notes if it's still listed incorrectly. If it is listed as phosphorus tribromide, leave it as is. That means you've gotten the corrected version of the notes. So phosphorus, P, 5 valence electrons. Tribromide, that means 3 bromines, 3 times 7 valence electrons. 3 times 7 is 21 plus 5, 26 valence electrons. Phosphorus is going to go in the center. There's only one of them. It's listed first. It's less electronegative. The electronegativity you may or may not be able to figure out from the general trend, but it is listed first, and there is only one of them, so it's going to be my central atom. Tribromide, I'm going to connect the 3 bromines around it. Notice I'm spacing them out kind of equally. I'm not just doing this to it. We want these spaced out. So space them out around the space you have around that atom. It's going to help when you get into VSEPR and actually start writing out the actual 3D structures of these compounds. So we've used up some of our electrons, but not all. Let's go ahead and give our outer atoms our octet. 2, 4, 6, 8, 10, 12, 14, 16, 18. If I add that to what's already been used, I'm up to 24 electrons. I have 2 remaining. I'm going to go ahead and put those in my central atom. Now I'm going to go ahead and check my overall formal charge. Bromine, 7 valence electrons, minus 6 lone pair electrons, minus 1 bond, gives me a 0 formal charge. Phosphorus is just like nitrogen. Phosphorus, 5 valence electrons, 2 lone pair electrons, and 3 bonds. When you have 3 bonds and 1 lone pair, it's going to give you a 0 formal charge. So this is the correct structure of phosphorus tribromide. What about chlorine trifluoride? This is telling me I have 1 chlorine. Trifluoride, tri means 3, so ClF3. Chlorine, 7 valence electrons. 3 fluorines, 3 times 7 valence electrons. So 7 times 4, 28 valence electrons. Got the chlorine and my fluorines. Give your outer atoms their octet. 2, 4, 6, 8, 10, 12, 14, 16, 18. Counting up what I've used so far, I'm up to 20, 22, 24. I've used up 24 electrons. I have 2 lone pairs going in my central atom. Notice I'm putting them in pairs in the central atom, but not next to each other. So I would not write like this. I'm not going to write them, all in a row. I'm going to separate them out so it shows 2 separate pairs on that central atom. It's really important as we get into the next unit. Now I'm going to check my formal charge. Fluorine, 7 valence electrons, minus 6 lone pair electrons, minus 1 bond, gives me 0. All of these fluorines have a 0 formal charge. The chlorine, also 7 valence electrons. The chlorine has 4 lone pair electrons and 3 bonds. Overall, also a 0 formal charge. I don't have to worry about resonance because resonance only comes into play when you have multiple bonds present. If you don't have multiple bonds, you're not going to see resonance. What about phosphite? Well, if you don't remember what phosphite is, remember phosphate is PO4 3 minus, and ate is 1 less oxygen but same charge. So if phosphate is PO4 3 minus, phosphite must be PO3 3 minus. My phosphorus, 5 valence electrons. My 3 oxygen, 3 times 6 valence electrons. My -3 charge, 3 more valence electrons. So 6 times 3 is 18, plus 5 is 23, plus 3 is 26. Connect my oxygens. Give my outer atoms their octet. If I count up all my electrons so far, I've used up 24 electrons. I have 1 pair remaining. I'm putting them on my central atom. Now everything has an octet, my central atom included. I'm going to check the formal charge. You're going to find very quickly when oxygen has, you got those 6 valence electrons. When oxygen has 6 lone pair electrons and 1 bond, I get a -1 charge. Phosphorus, we're going to find follows the trend of nitrogen. 5 valence electrons, 2 lone pair electrons, and 3 bonds give me a 0. So when phosphorus has 3 bonds and a lone pair, it will also have that 0 charge. Overall, my formal charge here, -1 plus -1 plus -1, is equaling the charge on the ion itself. That is my complete and correct Lewis structure. This also helps us see how phosphate comes from phosphorus acid, phosphite comes from phosphorus acid, or phosphate comes from phosphoric acid. Because these are all -1 charges if I was to make this a neutral compound. So if I had H3PO3 or phosphorus acid, it would be an oxyacid, where the hydrogens would bond to those oxygens. And now every species would have a 0 formal charge. So hopefully that helps you kind of see why they're oxyacids. It's the oxygen that's willing to give up or accept that proton back. SO2Cl2. So now we're just straight into formula. So we have to think about the formula. We're given the formula. SO2Cl2. S, one of them, 6 valence electrons. 2O, 2 times 6 valence electrons. 2Cl, 2 times 7 valence electrons. So let's see, 2 times 7 is 14, plus 12 is 26, plus 6 is 32. Sulfur is going to go to the center, connecting my oxygens, connecting my chlorines. Give everything an octet, or give all your outer atoms their octet. Technically, I've used up all my electrons. I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I've used up all 32 electrons. I've given my central atom its octet. I give my outer atoms their octet. All I've got left to do is check the formal charge. chlorine here. 7 valence electrons minus 6 lone pair electrons minus 1 bond gives me a 0 formal charge. Oxygen, 6 valence electrons, 6 lone pair electrons, 1 bond, -1 charge. Sulfur, 6 valence electrons, no lone pair electrons, and 4 bonds, +2 charge. So I can do some minimization of my formal charges here. The oxygen can each donate 1 pair of electrons to the sulfur. If I do that, I now see my oxygens have each a 0 formal charge. And if I look at my sulfur, again, 6 valence electrons, no lone pair electrons, but now 6 bonds. A 0 formal charge on the sulfur as well. So there is your Lewis structure for SO2Cl2. What about XeOF2? Xenon is a noble gas, so why is it bonding? Truthfully, it's so big it just doesn't care. Bonding happens with the very outer electrons, your valence electrons, and by the time you get to the size of xenon, it does not care what its outer electrons are doing. If they want to be involved in some bonding, go for it. They're so far removed from the nucleus that it doesn't really affect the overall behavior of the atom itself. Xenon has 8 valence electrons. Oxygen, 6 valence electrons. 2 fluorine, 2 times 7 valence electrons. 14 plus 6 is 20 plus 8, 28 valence electrons. XeOF2. Give your outer atoms their octet. I've now used up 24 electrons and give any extra electrons to your central atom. So I've now used up all 28. Now I'm going to check my formal charge. My fluorine, 7 valence electrons, 6 lone pair electrons, and 1 bond gives me a 0 formal charge for each fluorine. My oxygen, 6 valence electrons, 6 lone pair electrons, and 1 bond gives me a -1 charge on my oxygen. And my xenon, 8 valence electrons, 4 lone pair electrons, and 3 bonds. Gives me overall +1 on my xenon. Now, if I add up those overall formal charges, it does equal to 0, which matches the compound. But I can minimize this formal charge. Oxygen can donate a pair of electrons to form a double bond to the xenon. This gives us oxygen a 0 formal charge. And if I check xenon, 8 valence electrons minus now 4 lone pair electrons minus 4 bonds gives me 0 on xenon as well. And so by giving that oxygen a double bond to xenon, I have minimized my formal charge between the oxygen and the xenon. What about ASO3 3-? What is that called? Well, if I think about it, arsenic is right below the table and below phosphorus. And I know phosphite is PO3 3-, so this must be arsenite. ASO3 3-. AS, 5 valence electrons, 3 oxygen, 3 times 6 valence electrons, and 3 extra valence electrons for that -3 charge. 3 times 6 is 18, plus 5 is 23, plus 3 more is 26 valence electrons. Arsenic is going to go in the center, connected to my 3 oxygens. I'm going to give all my outer atoms their octet. I gave all my outer atoms their octet. I still have 2 electrons remaining, so they're going to go to my central atom. I now check if my central atom also has its octet. So everyone has its octet, so I can check formal charge. Now at this point, I've done this enough times to recognize that when oxygen has 6 lone pair electrons in one bond, it has a -1 charge. Arsenic, like phosphorus, 5 valence electrons, 2 lone pair electrons, 3 bonds, overall is 0 charge. So adding this up, -1 plus -1 plus -1 gives me that -3 charge of the arsenite ion. This is the complete Lewis structure of arsenite. What about POCl3? P, 5 valence electrons. O, 6 valence electrons. 3Cl. 3 times 7 valence electrons. 3 times 7 is 21, plus 6 is 27, plus 5 is 32. Give all of your outer atoms their octet. Check the central atom. It's got its octet. I've used up all my electrons. I've used up all 32. Everything has an octet, so let's go ahead and check formal charge. Chloride. 7 valence electrons, minus 6 lone pair electrons, minus 1 bond, 0 formal charge. Oxygen, again, up here I know, 6 valence electrons, 6 lone pair, and 1 bond is a -1 charge. And the phosphorus, 5 valence electrons, 0 lone pairs, and 4 bonds gives me a +1 charge. So I want to minimize that formal charge, and I can do that by oxygen donating a pair of electrons to form a double bond to the phosphorus. Now both my oxygen and my phosphorus have a 0 formal charge as well. Just a couple more to go. ClBr3, Cl, 7 valence electrons, 3Br, 3 times 7 valence electrons, 4 times 7 is 28 valence electrons. Cl to the Brs. Give all of your outer atoms their octet. 2, 4, 6, 8, 8, 10, 12, 14, 16, 18. And if I cut up what I've already used, 22, 22, and 24. That leaves me with 2 sets of lone pair electrons on my central atom. Let's go ahead and check your formal charge. Bromine, 7 valence electrons, minus 6 lone pair electrons, minus 1 bond. Overall 0 charge for each bromine. And the chlorine, 7 valence electrons, 4 lone pair electrons, and 3 bonds. 0 charge overall on the chlorine as well. So that is my valid Lewis structure for ClBr3. What about SO2 3-? Sulfur, 6 valence electrons, 3 oxygen, 3 times 6 valence electrons, plus 2 more valence electrons. 3 times 6 is 18, plus 2 is 20, plus 6 is 26. Sulfur is going to go to the center. Connect the oxygens. Give your outer atoms their octet. 2, 4, 6. I've already used 2 there, so 8, 10, 12, 14, 16, 18, 22, 24, 26. Or, sorry, 24. I can count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up 24 electrons. It is much more valid than what I just said. So I've used up 24 of my electrons, and I have 26 available. So what am I going to do? Central atom. I'll put it on my central atom. I'm going to go ahead and check my formal charge here. I know I should have an overall 2 minus charge. So oxygen, each oxygen here is going to have a negative 1 charge. Because I'm tired of writing that one out and it's up here. Each oxygen has a negative 1 charge. But does that mean that's everything? Well, let's check my sulfur. Sulfur has 6 valence electrons, 2 lone pair electrons, and 3 bonds. Overall plus 1 charge. I can minimize that. I can minimize that by an oxygen donating a pair of electrons to form a double bond. Now, sulfur has 2 lone pair electrons and 4 bonds, and overall 0 charge. This oxygen is 0 and the sulfur is 0. But why did I use that oxygen? It doesn't much matter. You could use any of the oxygens to form the double bond. These are resonance structures, and they are all completely equivalent. Overall, they equal up to negative 2 charge. The 2 individual oxygens have a negative 1 charge, giving that negative 2 charge overall. But I could also write this as S double bonded to this O, single bonded to the other oxygens. Don't forget that lone pair on the sulfur. I'll put the formal charges in just a sec. Or double bonded to this oxygen. Negative, 2 negative. This has a negative 1 charge. This has a negative 1 charge. 0 and 0. 0, 0, negative 1, negative 1. Again, these are resonance structures. And in this case, they all contribute equally. And only one more compound. S2O3 2 minus. 2 sulfurs, 2 times 6 valence electrons. 3 oxygens, 3 times 6 valence electrons. Plus 2 valence electrons. So let's see, 3 times 6 is 18, plus 12 is 30, 32 valence electrons. I have a sulfur central atom connected to another sulfur connected to 3 oxygens. Give all of your outer atoms their octet. This is technically everything has its octet. Let's go ahead and look at formal charge. Each oxygen here is going to have a negative 1 charge. Because again, I've done that up here a bunch of times on this slide. Negative 1, negative 1, negative 1. Sulfur is just like oxygen. If sulfur has 3 sets of lone pairs, or overall 6 electrons, and then 1 bond, it will also have a negative 1 charge. The sulfur in the center, 6 valence electrons, no lone pairs, and 4 bonds, gives me an overall plus 2. I can minimize that charge. What if 2 different oxygens donated their electrons? Too big. So now I've got, if I can jump so you can see him. Now the oxygen, one oxygen and one sulfur, each of a negative 1 charge. But these oxygens are 0, and if you do the formal charge of the central sulfur here, you're going to find it to be 0 charge. But why did it have to be those two to give the lone pairs? It didn't. Overall, I still have my 2 negative charge. But I could have said double bonded to this oxygen and this oxygen. Sulfur -1, -1, 0, 0, 0. I could have said, let's see, single bonded here, double bond here, double bond here. Giving me -1 here, 0, 0, 0, -1. These are all equivalent. But why does it have to be the oxygen double bonding to the sulfur? Why can't it be the sulfur double bonding to a sulfur? Because if the central sulfur can double bond, then the other sulfur can double bond as well. Now, whereas, let's see. Whereas these three are equivalent, this one is not equivalent to the other three. So if I compare these two, one will contribute more, one will contribute less. If I do the formal charge here, the sulfur is 0, oxygen is -1, -1, 0, 0. So again, the one circled in purple are equivalent. Those are contributing equally to each other. But between the purple and the one in green, which one's contributing most? On this one, sulfur has a -1 charge, and one oxygen has a -1 charge. On this structure, 2 different oxygen are -1 each. This is going to contribute most. And I could draw out the other structures here as well. I could say the double bond was here or here comparative to the sulfur having a double bond like I did in the other 3. But the purple is going to contribute the least. And why is that? Because sulfur is less electronegative than oxygen. And we want that negative charge to go to the more electronegative species.